Hi, we're going to talk about ring homomorphisms today. And this is Modern Algebra with Professor Gibbons. Now, you've taken a linear algebra class, and in linear algebra, we talked about these things called linear transformations. A linear transformation is a function L from a vector space to another vector space where you take addition in the domain and it gets sent to addition in the codomain. And you take scalar multiplication in the domain and it gets sent to scalar multiplication in the codomain. That is, u plus v gets mapped to L of u plus L of v. And c times v gets mapped to L times c of v. Got my letters backwards. C times L of v. Sometimes people say this preserves vector addition and scalar multiplication. Or more simply, people say this preserves algebra. Well, in modern algebra, we can generalize this idea. And we can think about functions between rings. Here's a definition. A function f from R to S, where both R and S are rings, is said to be a homomorphism, a ring homomorphism more specifically, provided, we want it to preserve algebra, which means we want to take addition in R and send it to addition in S, and multiplication in R and send it to multiplication in S. And that is, in fact, the rest of this definition. I take f of a plus b, and I should get f of a plus f of b. And I take f of a times b, and I should get f of a times f of b. And this is a way of saying that this is a function between these two rings that preserves the algebra. The addition in the domain works the same way as the addition in the codomain. So sums get sent to sums, and products get sent to products. I want to do some examples, and you know me, I like to do some non-examples too. So here's my first example. I'm going to take f as a function that goes from the integers to the integers mod 6. It's going to take a to its equivalence class mod 6. And I'm running through the calculations here. If I think about how modular arithmetic works, I know that I can take a plus b, and when I look at its equivalence, the equivalence class that I get from that, it's the same as taking the sets a mod 6 and b mod 6 and adding them together. Similarly, if I look at the equivalence class of AB, it's the equivalence class of A times the equivalence class of B. That's stuff we already proved about the way that modular arithmetic works. So, in short, that means that F preserves addition and preserves multiplication. So this is a ring homomorphism. Okay, if we we could do something similar. We could take G from Z mod 6 to Z mod 3 and take A mod 6 and take that representative and just put it in the brackets for mod 3. So take A mod 6 and send it to A mod 3. I think this is a ring homomorphism. I will at least attempt to convince you part of the way. But what I need to worry about is whether this is even a function. I have to decide if it's well-defined. If I take two different ways of writing down the same input, like 4 mod 6 and 10 mod 6, I need to make sure that they're both going to go to the same place, mod 3. And, not example, 4 mod 6 goes to 1 mod 3, and 10 mod 6 goes to 10 mod 3, which is also 1 mod 3, so that works out. So I need to prove that in general first, just so I even believe it's a function. So again, because we're working with equivalence classes in our domain, we want to make sure that it doesn't matter what representative we pick, the function's going to do the same thing. Well, I guess that is, the assignment is actually a function, which is another way of saying G is well-defined. So we want to make sure A mod 6 and B mod 6, if they're equal, the outputs will be equal. Okay, well, let's assume they are. That means that B looks like A plus a multiple of 6k for some integer k. And I can rewrite that then. I have that G of B mod 6 is going to give me G of A plus 6k mod 6, which gives me A plus 6k mod 3, which gives me A mod 3 plus 6k mod 3. And the exciting thing here is that 6k mod 3 divisible by 3, so that's 0. So that means that at the end of that calculation, I got A mod 3, and that's the same thing as G of A mod 6. So even if I pick different representatives, my function G is going to send those to the same place. I'm going to let you check that the addition and multiplication work out well. So you can pause this if you want to and check that G preserves algebra, or you can just continue merrily along with me as I keep telling you more about ring homomorphisms. Okay, example 3 here, I'm going to try to reverse the function I started with. I'm going to take z mod 6 and send it to z by taking the representative of the equivalence class and making that the integer that I get from h. Now, the bad news is, as tempting as this is not well defined. That's because 4 mod 6 and 10 mod 6 are the same equivalence class, mod 6, but h of 4 is 4, and h of 10 is 10. And 4 and 10 are not equal in the integers. That means this h that I've tried to write down, it's not even a function. It's just some kind of weird assignment. So that's my sad trombone noise. Womp womp. Okay, I've got one more. Actually, I think I have 2 more. I'm probably lying here. I've got 2 more for you. All right, let's look at the function k from the integers to the integers. I'm going to take a and send it to 2a. Now, I'm not working with equivalence classes here, so this is going to be a perfectly fine function. I don't need to check well defined. All right, but let's check that it preserves addition. Okay, well, if I take a plus b and I plug it into k, I get 2 times a plus b. I've got the distributive property. Cool, I get 2a plus 2b. That gives me ka plus kb. And that is good. That means that this preserves addition. When I look at multiplication, k of ab is 2 times the input, which is 2 times ab. But k of a times k of b is 2a times 2b, and that's 4ab. And that's not going to be equal almost ever, unless, I guess, one or both of those things are 0. If a and b are both 1, we get a nice counterexample. K of ab is 2, but k of a times k of b is 2 times 2, which is 4. So this does not preserve multiplication. We can go up to that blank in the top and write that this is not a ring homomorphism. Okay, last one, and this one is one that we'll come back to and use a bit in this course. I'm going to take f to be a subfield of the complex numbers. So it could be the real numbers, or it could be all of the complex numbers, or it could be one of those extension fields that we built that's the smallest subfield of the complex numbers that contains q and the complex number I and the real number square root of 2. This is going to work for any of those subfields. So I'm going to make a function that is take the conjugate function. And this is a ring homomorphism. We already actually showed all the math that we needed to for this. We just didn't have the function c in the middle. Back earlier in the course, we said that the conjugate of alpha plus beta is alpha conjugate plus beta conjugate. And the conjugate of the product is the product of the conjugates. So when we think about what that means for the c function, that means when I plug in a plus b, I get c of alpha plus c of beta. Sorry, I said a and b. I meant alpha and beta. And when I plug in the product alpha beta, I get c of alpha times c of beta. So this guy, this nice little conjugation function, preserves algebra. Okay, here is a theorem. This is a theorem that takes the definition of ring homomorphisms along with some properties of rings and allows us to say, okay, we know what the definition is, and here's some other stuff that has to happen. So I'm going to take f from R to S. It's going to be a homomorphism of rings. Then the following things are true. Okay, first one, f of the additive identity of the ring R will be the additive identity of S. This says 0 gets sent to 0. And depending on what my rings are, maybe my ring R is a ring of matrices and my ring S is a ring of polynomials. That's saying the 0 matrix goes to the 0 polynomial. It's like whatever that 0 object is in the domain, it's going to go to the 0 object in the codomain. And luckily, we know both of these things exist because we know that rings have to satisfy the axiom that says, hey, there's an additive identity. And we also know from properties of rings that the additive identity is unique. K2 says additive inverses get sent to additive inverses. So if I take an element A in my ring R, it has an additive inverse, which is unique. We call it negative A. And this says if you plug in negative A to F, you're going to get the additive inverse of the element F of A, which is an element of the ring S. So additive inverses in your domain gets into additive inverses in your codomain. That's basically saying that if A plus B is 0 in R, then F of A plus F of B is going to be 0 in S. Now, if we're lucky enough that R and S are division rings, that means that we can prove the same things for the multiplicative identity and the multiplicative inverses. Now, remember, a division ring is not necessarily commutative, but we do have multiplicative identity. So R and S both have a 1 or a unity. And we know that every non-zero element has an additive inverse. And I guess I should say, I wanted to be a little bit careful. F from R to S, where F just sends everything in R to the zero element of S, that is a ring homomorphism. I was going to say, oh yeah, we've got to be careful that we're not going to 0 and S. But hey, if we do, it's the 0 ring. And yeah, 0 is its own multiplicative inverse. That's a little bit weird. I guess that would mean S can't be a division ring. So we should probably specify. Let me add here that and F of A is not equal to 0S if, A is not equal to 0R. So we just want to, I guess we just want to be a little bit careful that we don't send stuff to 0. But it basically works the same way when those proofs will look very similar. All right, so I'm going to prove parts of this. I'll prove one. If I take f of 0r, I'll use my favorite algebra trick to say that 0 can be rewritten as 0 plus 0. So the input 0 is the same as the input 0 plus 0. And because f is a ring homomorphism, it preserves algebra, which means that f of 0 is equal to f of 0 plus f of 0 when I expand that first equation. And now S is a ring, which means that f of 0, which is an element of S, has an additive inverse. And I'm just going to call it B to make the notation less terrible. That means there's something I can add to the element f of 0, which lives in the ring S, to get the 0 of S. And if I add that to f of 0r and then f of 0r plus f of 0r and use the associative property, I'm able to cancel off an f of 0r from each side. And I see then that means that 0s is equal to f of 0r. Cool. For part 2, f of 0r, I can rewrite as f of a plus the additive inverse of a. And then I can break that up by the definition of a ring homomorphism into f of a plus f of negative a. Well, part 1 says that f of 0 was 0s, and now I see that f of negative a satisfies the definition of the additive inverse of f of a. And that means that f of negative a is negative f of a. Cool. Okay, 3 and 4, they look a lot like the proofs of 1 and 2, but using multiplication instead of addition. So you might find it helpful to use that 1 is 1 times 1, and that 1 is a times a inverse. All right, so here's a definition. If I take a ring homomorphism, f from R to S, then the kernel of f is all the stuff that goes to 0. It's the set of R and R, where f of R is 0s, and that's a subset of the ring R. And the image of f is the set of stuff I can actually get to by plugging things into f. So that's a subset of the ring S, and it's all the S that looks like outputs, where I've plugged something into R and arrived at S. Now, I always draw myself a little picture. I've got R and S. I can think about how the kernel of F and the 0 of S are related. The kernel is all the stuff that gets sent over to S. And then I can think about how the image of F and all of R are related, and the image of F is everything that I get when I plug in all of R. Okay, so the kernel is what goes to 0, and the image is what you can get as output. And let's look back at our examples. The first example, we took integers and sent them to their equivalence classes mod 6. Well, the kernel here is every integer where f of a is 0 mod 6. And that means that the equivalence class a mod 6 should be the same as the equivalence class 0 mod 6. And we know what that is. That's the set of stuff that's divisible by 6. We also just talked about ideals and principal ideals, and it turns out that that is our friend Langle 6 Wrangle, or the principal ideal generated by 6, all the multiples of 6 in the integers. Now here's a cool theorem that I will ask you to prove as part of your writing assignment at some point. Given a ring homomorphism from R to S, the kernel of F is always an ideal of R. So it wasn't an accident here that we saw that we got the ideal generated by 6. Now, if we want to think about what the image is, we're curious to know, like, if I take something in the codomain, can I get there? And given an equivalence class A mod 6 in the codomain, I just need to take the representative and plug it into F. And I'm like, cool, that's an integer. So that's allowed input, which means that the outputs I can get to are all the things in Z mod 6. That means the image is Z mod 6. And there's another theorem here that says for any ring homomorphism F from R to S, the image of F, it's not quite as good as an ideal, but it will at least be a subring of the codomain S. Okay, we did the same kind of thing. We took elements of Z6 to elements of Z mod 3 by just swapping the brackets, basically. And the kernel here is all the things mod 6 that get sent to 0 mod 3, which works out to be 3 and 0 mod 6. And again, the image of this homomorphism is going to be Z mod 3, because given a target equivalence class mod 3, I can just take that representative and pop it in the mod 6 brackets, and that works out just sort of nicely for us. So this is another example where the image is the whole codomain. They won't always happen, and you'll see some examples where they don't, but I think all the examples that I picked today, the image ends up being the whole codomain. Okay, we had 2 non-homomorphisms, so our next example here was 5, which is conjugation. Conjugation, the kernel is every complex number whose conjugate will give us 0. So if I take a plus bi in F, then a minus bi should be 0 plus 0i. That means a and b both have to be 0. Now, okay, if this is just the subring of the real numbers, then b is always 0 anyway, and that's okay. That's just saying, like, okay, well, now the real part also has to be 0. But the kernel of conjugation, whichever subfield of the complex numbers we pick, is going to be the set that just contains 0, and that is an ideal. That's the principal ideal generated by 0. The image of C is all the stuff I can get to by conjugation, and if I give you a target alpha in the codomain, you're like, okay, well, if I plug the conjugate into the conjugated function, then the conjugate of the conjugate is the original thing, and that means that I can arrive at it from plugging in its conjugate. So the image, again, is all of F. All right, we're at the last slide here. If a ring homomorphism from R to S is injective, which is a fancy way of saying one-to-one, and surjective, which is a fancy way of saying onto, then we say that F is an isomorphism of rings. We also write R is isomorphic to S, and we say it as R is isomorphic to S with that little equal sign with the squiggle on top. If you're latexing this, by the way, that is the /CONG latex command. To show that R and S are isomorphic, typically we have to build the isomorphism between them. So if we've got this nice ring homomorphism that's one-to-one and onto, then we say it's an isomorphism. The word homomorphism means similar shape or similar structure, and the word isomorphisms means same structure or same shape. So here's some homework for you. Prove that given a ring homomorphism, F from R to S, it's injective if and only if its kernel is just 0. There's nothing interesting in the kernel. The only thing that's in there is 0. We know 0 has to be in there because 0, by our properties of ring homomorphisms, goes to 0s. And the definition of surjective essentially says that the image of F is all of S. If you forget off the top of your head the characterizations of injective and surjective, here's some reminders. Injective means that if you have 2 outputs that are the same, then the inputs that you use to get there must be the same. Or if you take the contrapositive, it says if you start with different inputs, you get different outputs. It's kind of the flip side to being a function. A function says if you start with the same input, you get the same output. Or if you get different outputs, you must have had different inputs. So it's the converse of being injective. And surjective says, given a target in the codomain, so like for all Z and S, there's some element A and R where you can plug A in to your function F and get to Z. That is all I wanted to tell you about ring homomorphisms. I guess I should point out that example 5, we found that the kernel was 0. The conjugation map has a kernel of 0, and its image is all of the codomain. So we call that an isomorphism. And in fact, we'll talk later about these special isomorphisms from a set to itself, a field to itself in particular, and those are called automorphisms, which means it's an isomorphism onto itself. So it's got self-structure or something. I'm not a Greek scholar, so I will leave it at that. And we will come back to the idea of homomorphisms later in the course when we're trying to count some stuff about how roots of polynomials get swapped around, because we're interested in finding roots of polynomials. All right, bye guys.